Alright, welcome to another video. This is going to be in the Wild Networking series. It's going to be reading the Cisco Campus LAN and Wireless Design Guide. Last video, I set up one of the more legacy designs, kind of a traditional way to design it. I mean, it's not, there's probably a lot of these sorts of designs out there right now, but in this video, we're going to be reading about the modern day current recommended one according to this guide. The legacy design has a combination of layer 2 and layer 3 links like this. So we set it up. We also set up VRRP. And we set up VRRP load balancing as well, so that we had a collection of ports on here, or we had two PCs. One was configured to go up this link, another was configured to go up this link. But when I shut down one of these, the one that was configured to go up this link now knew to go over here because of the default gateway IP being a VRRP virtual IP. One issue we did have though is the VRRP traffic was going through these links and not this layer 3 link. In fact, we could have just taken away this layer 3 link and it would have made no difference in our topology. Ideally, that VRRP traffic goes over the layer 3 link, then you can preserve bandwidth here. It actually is quite a bit of extra chatter we saw on the line due to VRRP. But this video, we're going to be looking at the modern day designs and moving on past those legacy designs. So this is layer 3 routed access campus design. In another approach to access and distribution layer design, you can use layer 3 beyond just the core and distribution layers and configure layer 3 all the way into the access layer. Using the layer 3 access design removes the layer 2 to layer 3 boundary at the distribution layer and makes each access switch the boundary between the layer 2 access ports and the outbound layer 3 connectivity. The benefits of this design are that you eliminate spanning tree loops and reduce protocols because the IP gateway is now the access switch. I guess I'm not sure what they mean by reducing protocols. Because there are no spanning tree blocking links, you can use both uplinks to the access layer and increase effective bandwidth available to the users. This design makes it easy to maintain configuration consistency while providing excellent convergence properties with minimal tuning, as the more complex layer 2 interaction at the layer 3 distribution is eliminated. The challenges with the routed access layer design is that the layer 2 domains are confined to a single access closet, which limits flexibility for applications that require layer 2 connectivity that extends across multiple access closets, and access switches must have the capability to support the layer 3 routing functionality, and differences in IP addressing and subnetting must be accommodated. Many organizations have been unable to overcome the application requirements, driving the need for layer 2 connectivity across access layer switches, resulting in the desire to address the needs using alternative designs. Okay, so let's set up this next one. In this next one, we've got every link is a layer 3 link. Now that's going to be a little tricky to do. We can't do it exactly as shown there, where I put an IP address on the actual link, because our extremes don't allow for IPs on the actual links themselves. You have to put it on a VLAN interface. But you can assign a VLAN to a single link, a single VLAN to a single link, and basically simulate as if it were on the interface itself. Okay, I have a really hard time keeping my place in this document. Oh, here we go. Okay, this looks familiar. There we go. So, alright, so I'm opening my lab. I might need to change into a t-shirt. I'm going to do that. I'll be back shortly. Alright, so my lab is now booting up. We're going to convert what I have here. Now we're going to convert it so that the L2 to L3 boundary is on the access layer here. Right now, we have an L2 to L3 boundary on the distribution layer. So these routers, if I open it and I do a show IP route, what am I going to see? Okay, so it's booting up, but what I'm going to see when I do a show IP route is either no IP route table at all, because I don't even need to enable IP routing, or just an empty table, since there aren't any IP addresses on here. And one thing I do need to say, I watched a little bit of my last video, and I was kind of giving damnation to extremes for requiring that command to enable routing. I thought that was a little bit unfair, actually, going back on a lot of other kinds of equipment, like Cisco, pretty much any kind of equipment. That kind of command is also necessary on Cisco. If you want to use IPv6, you need to do the command IPv6 unicast routing. I think you might even need the command IP unicast routing if you're on a layer 3 switch to enable a table. So that was a little bit unfair to extremes. Their devices really aren't any more cryptic or difficult to configure than any other vendor, at least in my experience. And the documentation I found was really helpful and really good. So I just wanted to make that clear, that when I was saying, when I was expressing frustration with the extremes, going back and looking at, I just wanted to make it clear that seemed a little bit unfair, because a lot of other kinds of equipment require you to actually explicitly and manually turn on the routing table if there's multi-layer capability as well. It's not just extremes that require that. So it was more my own newness to the extreme that was the problem, not the extremes themselves, especially since the documentation was so easy to read and easy to find online. Okay, so let's see here. We've got, so let's do that command, show IP route. No IPv4 routes configured, and that makes sense because we have our layer 2, layer 3 boundary here, so we don't have any IP routes here. This is all layer 2. So instead of a routing table, everything is in the MAC address table. That's the only way traffic is moved across this device. It's purely at layer 2. Layer 2 uses MAC addresses instead of IPs. So there's no IPs to be found anywhere on this device because it is purely in a layer 2 domain, and the edge of that domain is on the distribution layer. So what we're going to do now is we're going to change that domain edge to be on the access layer. So we're still going to have layer 2 interfaces, but those are going to be the interfaces connecting into the PCs. Every other interface will be a layer 3 interface. So these interfaces here connecting into the PCs are going to be on the edge of these interfaces here, which are layer 3. So we're going to have a boundary between these interfaces down here and these interfaces up here, where these interfaces are layer 3, but these are layer 2. And that's different than up here, where we had this interface here be layer 3, and these down here be layer 2. Now we're going to have all these interfaces layer 3. This whole access layer is now layer 3, no layer 2 to be found. So we can have an empty MAC address table on the distribution, because we'll have ARPs, and we would have an empty MAC address table if I could figure out how to make these routed ports, but it looks like it doesn't support that. So we will have a MAC address table now, but it'll just be there'll just be like one entry in it, which is the MAC address on the other side. Okay, so let's waste no time here, and we're gonna configure this to all be layer 3. We'll need an IP address for all 3 of these links. So if all of these links are going to be layer 3 links, they each need their own IP address. So the scheme we'll use is 192.168.1.1. Let's do it this way. So we're going to have .0 up here, 1, 2, 3, 4. Yeah, I think that's going to be fine. Yep, okay, that's what we're going to go with. So let's start with the extremes. Okay, so we're not going to need, actually we probably could still have VRRP. Yeah, we could still have VRRP on there, but for now let's get rid of VRRP. Okay, and then we'll get rid of these VLANs as well. We're gonna start a new VLAN scheme for this. So delete VLAN. Yep. All right, that looks good. So now I'm going to save that, and yeah, let's clean up the other one before thinking about the configuration, then I can put it in a Notepad++ file and reuse what I put in this first switch as a template for the second one. Oh, so I gotta delete VRRP first. Alright, perfect. So, yep, so now we need Notepad++. Okay, and then we need, what else do we need? I can't even. Oh, right, we're gonna need Vlans. So let's keep our, so we need point-to-point. Now we can use /31s. There's a special RFC that allows for that most equipment supports. But let's just go with the traditional /30s, even though we're wasting space. Now we are going to need a routing protocol as well, because otherwise this switch here won't know about this link or this link, and we want, I believe we want it to go there. I'm a little bit confused about this. Alright, but anyways, let's pick out our VLANs. So, we're going to use contiguous space here. We're going to use 168 dot 0.0 4 8 12 and then dot 16. Okay, so we've got 5. So now we've got to pick out VLANs. VLANs, we don't need to worry too much about what our scheme is. It doesn't have to be contiguous or anything like that. The IP space, it's definitely better that it's contiguous. Otherwise, you break apart. You make your IPs harder to work with, and then harder to summarize too for your routing protocols. So, okay, so we're just gonna go with 10. 20, 30, and unfortunately I have to do this because so some of these I won't have to use VLANs, so we'll worry about that when we get there though. So yep, so the first 3 links we're gonna configure are here on our first distribution layer switch. Okay, so create VLAN, and we're going to call this VLAN 10. Let's call this, VLAN 10 dist to dist. Oh, I gotta give it a tag. Is it gonna let me? It's gonna reject it, right? I'm gonna get an error because I didn't give it a tag. No, it allows me to do it without a tag. Okay, well, I'm gonna delete it and recreate it because I want it to have a tag. And I want the tag to be 10, not 30. Where did 30 come from? Okay, so now we can configure it. And this is our distribution. We definitely want an IP address on it. It's going to be 92.168.0.1/30. Alright, and then we got to add ports to it. So show LLDP remote. Or neighbor. There we go. So we can see our neighbor. Our other distribution switch is port 3. Perfect. So that's all we need to do for now for VLAN 10. So so VLAN 10 was here. Let's do VLAN 20 down to the access switch on the right. So we'll say, and I want to take notes. This 2, we'll say access 2, and then this is going to be access 1. Okay, so we got one more, VLAN 30. This goes to the access layer as well. Okay, so everything looks good. Yep, so here's our VLANs. Yeah, everything looks pretty darn good. Oh, it looks like we're missing IP forwarding on VLAN 30 though, because we've got to enter that every time we create a new VLAN. We've got to do this enable IP forwarding. Otherwise, there won't be IP forwarding on that new VLAN. Okay, now we will need a routing protocol as well. Otherwise, we won't know what to do for traffic destined here or destined here. But at the same time, you know what? Honestly, we actually don't need that, because we don't want our users down here to access these. So it's okay that it doesn't know about these, because it's only meant to access the stuff off our access layer. So for management, if we plug into the distribution, yeah, we might want to know about these, because if this link goes down, we still want to be able to access this in band. But for now, I'm going to leave a dynamic routing protocol off and just have it route based on the directly connected routes, because we're only going to be concerned about being able to ping from one PC to another. Okay, so let's take a look at the diagram and try to figure this out a little better here. Looks like it's 729. All right. 729. Oh. Okay. Let me think here. So, what have I got? Oh, yeah. So I've got VLAN 10 here, VLAN 20, and VLAN 30. So we're gonna go with VLAN 40 on this link and VLAN 50 here. So that means we still got VLAN 10. That's good. This is .2 on VLAN 10. Yep, and it's port 3 still, added to VLAN 10. But now, port 4 here, that's going to be 10, 20, 30, VLAN 40. So let's find, yep, so here's added to port 4, so let's highlight this. Okay, so this is going to be port 40 now, or sorry, VLAN 40 now. Okay, and then the IP address is going to be different. Instead of .5, it's going to be, we'll go with .13. Perfect, okay, and then 30, so 10, 20, 30, 40. Now we're using 50 instead of 30. Excellent. That is perfect. Okay, so the next step is to change the IP now. So this is going to be dot 17. Perfect. Yeah, that looks good. Yeah, that looks really good. Excellent. Okay, we are good. Okay, so let's see here. Next is going to be the access layer. We've got the distribution layer set up. Let's do a quick ping, make sure we can ping across the distribution to distribution VLAN. So that is going to be VLAN 10. So VLAN 10 is configured with an IP here. So we're on this first one here. So to ping to the second one, we got to ping to .2. And we're good. So as I said, now if we look at the IP route table, we've only got these directly connected routes, these direct routes. Oops, and it looks like I accidentally, yep, so but the thing is I didn't save it. So I'm gonna make my life a little bit easier, and I'm just gonna reboot it so that I boot up to the starting config, which doesn't have those changes. I reconfigured the first distribution switch with the configuration meant for the second one by accident. So this is going to be the easiest way to undo that nightmare. Okay, and then we'll keep a running ping on there. Hopefully that, yeah, if this comes up with .1, that'll be good enough for me because I reconfigured the other side to .2. So, can I not just continually do it? Isn't there like on-box Python? Oh, there's not. Some of these have on-box Python, and that's awesome when they do. Ooh, I can do a start maybe. Oh, that might. Okay, so I can run a script here, but I want, yeah, so I can run Python files, but I can't just open a Python interpreter shell. That's the holy grail for me. And you can do it on Aristas and Dells, but I don't think you can do it here. No, you can't do it on this. But I could make a test.py. See, so I can run Python on it. Oh yeah, bye. Oh, sweet. Okay, it's kind of like Linux. Yeah, it's just a Linux. So I wonder if I can do. Nah, I can't do other Linux commands. All right, but let's see what we got on this site. Oh, looks like I'm not sure what's going on. Okay, perfect. We're good now. Perfect. Okay, so I can ping it now. We're good to go. Yeah, so now the next part is going to be configuring the access layer. We don't need to configure the a routing protocol unless we want in-band management to plug in for in-band management on the distribution layer. We'd want that, but right now we're just concerning ourselves with the end users, so we're not going to need that. So as it is, we've got VLAN access 30 on everything, so we're gonna start by removing all of that configuration. So we'll do a default on all of the interfaces. Okay, and we can do no VLAN 30. All right, so now we've got just a blanked out generic config except for LLDP. Should still have LLDP name ready info, and we do. So I'll just save that. So now what we're going to do is create our layer 3 boundary by configuring these two links, and we've got an extra option on these Arubas. Makes it nice and easy. We can just use a routed port. There we go. So now we can add an IP address to the port. And this is going to be VLAN 10, 20, 30. So this is going to be .10. Perfect. Okay, and then this will be 10, 20, 30, VLAN 40. And it'll be .14. Perfect. All right. Huh. You know what? We are going to need a routing protocol because when we send first of all, we're going to need to choose a default gateway. We're going to need to choose either this link or this link as the default gateway. So we're actually not going to be able to load balance these links. I mean, we can load balance it in the same way we were load balancing it here, where we have one PC choose one link, one PC choose the other link, and then you can load balance like that. That's something you can't do with a layer 2 domain only. But we have to have a dynamic or configure all the static routes that we need. But I'd rather just use a dynamic routing protocol, because we are going to need to learn. So if we send a packet to PC2 and our default gateway is on this network, since PC2, since there's a layer 3 boundary here, now I'm confused. Well, let's just keep going. I'll figure it out as I go. It'll become more clear as I look at the network. All right. So, okay. Yep, so now it's time to configure the links here. 111 goes up to this router here. So that's VLAN 20. It's going to be .6. And now this is VLAN 50, and it's going to be .18. Alright, so those are our layer 3 links. Yeah, so now we need a layer 2 domain, a boundary for layer 2. So to do that, we've got to create a VLAN, local area network, for our layer 2 domain. So we'll call it, I guess, 200, or let's name it 100. Yep. Name L2 boundary. Okay. And now we need it to be able to interact with our L3 boundary. So how do we do that? We make a VLAN interface on it so that traffic can be routed between these boundaries. Okay, and then we need IP addresses. So let's go with 10.0.0.1/8. Then no shut. Okay, now let's do it on this side, and let's not go with let's not use this IP. Instead, let's do IP address 10.0.1.0.1/8, or sorry, it's /24. Let's do 10.2.1/24. There we go. All right, and then here, hopefully this is clear what I need to do here. So I'm going to do VLAN 100, name L2 boundary. So you might be thinking, oh, well, how can I use VLAN 100 on this side? I used it on the other side. Well, VLANs are locally significant. They're only meaningful on the device they're configured on, even though traffic can be sent with a VLAN tag. So that tag doesn't say, here's a tag, now you do this. What that tag does is when a device receives it, it says, I see a tag, so I will do this according to my configuration. You do not tell a device what to do based on the tag you send it. The device takes actions based on its configuration depending on what kind of tag it was sent. So hopefully that's clear. I understand if that's kind of, if I didn't quite get that across. It's a really fine distinction, but it's important to understand that VLANs are locally significant, VLANs are locally significant. If you don't understand that, you can end up really kind of getting into a jam with VLANs and having them do things you haven't expected. So because these are locally significant, we don't need to have unique VLANs across these two devices. We can use the same VLAN. That's not true for IPs though. IPs are not locally significant. So we have to have a unique subnet on these two devices. Okay, so now we need to add VLAN 100 and we can just have an access port. That's totally fine. So let's do that. Oops. Now I'm not sure which port it was. Was it? Oh, right. I've got two of them hooked up. So this is port 9, which is port 8, and port 7. So now we do no routing. Okay, and then we'll do a no shutdown right away. And then we'll do VLAN access 100. We'll do that for 118 as well. Perfect. Alright, perfect. So yeah, everything should be good now. Last step, well, we might have one more step actually. Let's try it with this step, but oh, you know what? No, because even though this is a layer 2 domain here, it still has a subnet associated with it, and it has to, otherwise it wouldn't be able to communicate with any of these other links. So when we send traffic out, we send it to the default gateway of this subnet we're on, this broadcast domain here. So this layer 2 section. So now it needs to know how to get here, and we can see it's not directly connected there, so it's not going to know. So we do need to set up either dynamic routing, static routing, some sort of routing we need to set up on all 4 of these, because none of these here, except for this one, knows about this one. This is the only one that has a directly connected route for this network, so all 3 of these need to know about this. Okay, so let's use just basic single area Ospf. Kind of tempted to just use RIP. But let's use Ospf. And we'll just put everything in area 0. Okay, and then we need to, on the Vlan interface, Vlan 100, IP Ospf 1, area 0, and then on each of the links as well. And I guess we could make it in area 100 here and then area 200 here, and just have area 0 be there to kind of show more that we've got a boundary, and then we can, as we expand out as we scale this thing up and we add more to our access layer, more of these switches, now our area 0 is not expanding up quite as much. So that's probably a little bit of a better way to do it. But we're gonna go with this way, even though it's not the best way for now. We just want to get traffic pinging across the networks because we want to keep reading more of the guide. I forgot the process ID. Okay, so now we're going to need to add Ospf to these as well. If I do a show IP route, see we don't have any Ospf routes yet, we just got connected in local. That's because if I do a show IP Ospf or show Ospf neighbor, or show IP Ospf, yeah, neighbor, we don't have any neighbors yet. We haven't configured anything across these links. Perfect. Or I might need to create it. Yep, we got to create an Ospf area first. Oh, and we got to give it in the full. There we go. Oh, okay. We've got to. We can't just add it to ports. Let me try this. Configure ports, or sorry, configure Vlan 10 protocol. Oh, that's a filter. It's not it. Add. No, can't do that. Okay, we got to do it the hard way. So, okay, so we're using this, so we can, let's do this. So configure protocol Ospf. Or configure Ospf area 0.0.0.0. Oh. Okay, we can do. Oh, maybe I can just do it as easy as that. So what kind of, I have 10, 20, and 30. Now I should have some neighbors, I should have some Ospf routes now, so let's do a show Ospf neighbor. Don't have any. So yeah, I don't think that was the right way to do Ospf. Oh, now it's. Now it is. What does this mean? 663. Oh, I think that's for summaries or something. Oh, I can add neighbors. Ah, that's a sucky way to do it. Oh. Why couldn't it add the neighbor? There is no Ospf configuration. Yeah, still don't see it. Still not showing up. Okay, now we've got it enabled. All right, let me go back to that quick configuration guide and see how to set up Ospf on this. Here we go. This is the PDF I was looking at before. Okay, so the following commands are commonly used for performing OSFP operations. And hopefully that's the same as Ospf, it's just a typo. So let's give this a try here. So I think we were just missing the router ID. So configure Ospf router ID. Yeah, we'll just do 191. Oops, there's no dash. Cannot change. Okay, what about disable Ospf? Ospf router. Looks good. Okay, and then enable. And then create Ospf area 0. Okay, and then I'm not gonna. Oh, you need a full core to change the priority. That's fine. To turn on Ospf for VLAN, perform these steps. So we're going to do configure Ospf, add 110, area 0000, enable Ospf. Okay, that's to turn it off, so let's take a look at the status. Yep, everything looks good to me. Let's see if we've got some neighbors. Don't have any neighbors yet. Okay, so let's do some T-shooting then, because we should have a neighbor with the Aruba here. This is -7, yep, so there it is. So Let's try to ping across the wire. Dot 9 is going to be the... Oh, so already we got a problem here. We can't ping 9. Okay, we do have it set up here. We do have dot 10. Alright, let's try pinging dot 10 from here. Timed out. Host unreachable. Okay, so let's do a show. Now let's see if... So this is VLAN 30, so... oops, so I think I see the problem here. This is supposed to be VLAN 30. So VLAN 30 is meant to have port 4, 20, port 5. So this is the problem here. So luckily that's not too hard to fix. Yeah. Okay, so we should have better luck now. Let's try to ping 68.0.10. Yep, we got it. So let's see if we got an Ospf neighbor. Got it. We actually have 2 Ospf neighbors now. Right, because we also fixed port 5. And we already set up Ospf on these, because this is where this is the easy ones. I'm used to configuring Ospf on that kind of device more. All right, so yeah, it's going to be just as easy. So let's try it here. Yep, we just need a different router ID. Oh, right. Okay, we've got different VLANs on here. So I think we've got 40 and 30, or 40 and 50. Perfect. Okay. All right, so we've got, oh, it looks like we've got 3 neighbors. Perfect. That's the amount of neighbors we'll have. So now, since we've got it configured on this other one, we'll have 3 neighbors on here as well. On these access layer switches, though, we're only going to have 2 neighbors because we don't have a connection to the other access switch. Yep. All right. So, yeah. Okay. So now we've got all the Ospf routes that we could possibly want. Yep, so we've got 1, 2, 3, 4 routes. Let's Yep, so of course we know all our directly connected routes. So 1, 2, 3, 4 routes are all the routes we're going to need. So perfect, we're good. So so the final step is going to be setting up the IP, the PCs. And we could make this a passive area in Ospf. We could also make it a separate area, a stub area. Lots of things we could do, but we're going to keep it as simple as possible here and try to move on quick so we can get more reading in. Okay, so it's got to fall under the same subnet. 10.0.1.0/24. So we'll give this one 200/24. Yep. And then we'll need to give it a gateway as well. That one. There we go. Okay, and let's see if we can ping between the two here. We can, perfect. Give this 100. All right, so yeah, that's all the evidence we need. Let's take a look at some of the links to determine where the traffic is going. First thing we're going to do is sniff this link, and we'll see if we've got ICMP traffic on that link. I'm going to stop this and give it a few more zeros so I know it won't stop as I'm trying to look at the traffic. So right now we've got traffic coming up from PC2 here, so we're going to see if it goes over this link, or for that matter, if it load balances. Okay, so here's my capture of the link on the right here, filtered out for ICMP. Nothing captured, nothing at all. There we go. So we can see all of the traffic went over to this link here. Yeah. Okay. Huh. I'm just trying to think how we can have like a load balancing scenario. Because we can't really do like VRRP the same way. Like, I'm just trying to think, like, what's the advantages of this design over the other one? I guess you get Ospf, which is Dynamic Routing Protocol, in the works, which makes things a little bit better in some way. You know what? I'll show you. I'll show an advantage. So, in some of the other. Yeah, so I don't even have a, so we know the traffic is going up through here. Well, let's open this console. Okay, so make sure this is saved. Yep. So we got real simple config on here. Just IP addresses, just the dynamic routing protocol. IPs on every link. Here we had to do it with a VLAN over this, so we couldn't put it on the port itself, but we basically simulated that. So we don't have VRRP, don't have anything. So we're screwed, right? If I do this, that's a really bad thing, right? Huh. Huh, I actually thought it would, so I think eventually it will kick in once those neighborships expire. Yeah, I thought it was gonna, okay, yeah. I confused myself for a while there. So, and now we can see our capture here, we've got nothing going. But our capture on this link here, port 5, -4 to -8, this link here, now we are getting ICMP. So we can see even without VRRP, we have built-in failover. We didn't even have to use an extra protocol. We can just rely on the dynamic routing protocol to switch over to the live link once the neighborship fails. So start this again. Now we might lose some traffic if it switches over. I'm actually not sure what's going to happen here. I'm curious. All right, so yeah, it's fine now. Everything is there. So let's take a look at the routing table on -3 here. Oh, and it's got a attempt to reach out to a AAA server in timeout. So I think it's default like 30 seconds or maybe a minute. I don't think it's like 5 minutes, anything like that. But the final thing I'm going to do is tank a device again. Yeah. And take a look at the inner workings. So this is -3. We're going to tank the other device. And I don't get why don't I have my... Oh, I do, okay. So show IP route. Can I get like protocol or something like that? Origin, filter. I can always do a pipe, grep, and then we're gonna look for, yeah, #O. Incomplete command. Oh, there we go. Okay, so now we're just looking at our 4 OSPF routes that we need. So the last thing I'm going to do is cut that other one and then kind of keep running these commands, show OSPF neighbors, the other one, and then we'll see the traffic switch over. So I'm going to get these 2 captures more prominent. we go. This one as well. There we go. Okay, so we see that the -4 to -8, this link here is nothing is going over that one anymore. It's all going over the -8 to -3 link here. So if I shut this one down, nothing's gonna happen. So I will shut this one down again. So we're going to look at the one I'm not shutting down here. And you know what would be the most interesting one to look at? I think it'll be this one here, because right now it's deciding to. So yeah, let's do this. We're going to do show IP routes. 10.0. 1.0. There we go, and now we can see we've got cost equal paths, but I don't think we have load balancing turned on. Bluetooth. Ooh. That is interesting. I think there's a way to turn on load balancing for equal cost paths. Let's look that up. Yeah. Okay, so it's IP load sharing. So it's going to be under router Ospf 100 or Ospf 1 IP or there we go. So it looks like this is already enabled. I'm confused here. See, I wanted to load balance so that each of these are incrementing. Right now, only one is incrementing. And it is a cost equal path. So I'd like to see one of those increment. I'd like to see both of those increments. It's all enabled. Alright, well, I'm not sure what's going on. Okay, but let's just take a look at this IP route, and then oh, heck yeah. OVS. All right. Anyway, I'm done messing with that. So, okay. So let's just do it. We're gonna tank this one again. Leave this one open. Take a look at how the routing table changes on this device here. So you can see we still got cost equal paths now. We still got two neighbors here. So we've got dead timer due in a certain amount of time there. So yep, the dead timer isn't being refreshed, so it's continually decrementing, and now it decremented all the way down to 0. So looks like it went back up though. So it did get one. Oh, okay, it dropped off now. Okay, so we're down a neighbor. No longer have a route through this link, so now we're sending out this link. So just based on the routing table at the edge, you can have pretty darn nice failover times. You know, nothing like the 1 or 2 packet lost scenario we had with VRRP, but that required pretty complicated VRRP configuration. So just for free, without any extra config, if you design your network so that it's layer 3 throughout, you get failover just automatically without an extra protocol like VRRP. And that's what they meant when they said that you can reduce protocols. So where did they say that? They said that up here a bit. I keep losing my place in this doc. It's really annoying. Oh man, I've got a lot to read on this. Okay, yeah, up here. So, yep. So we get convergence properties with minimal tuning. You can saw that. We saw it converge when there was an issue there, and we also reduced protocols. We didn't need VRRP anymore because we automatically get that with the decisions made in the routing table. All right, so next section is preferred layer 2 access using a simplified distribution layer campus design. An alternative that can handle layer 2 access requirements and avoid the complexity of the traditional multi-layer campus is called a layer 2 access with simplified distribution layer design. The design uses multiple physical switches that act as a single logical switch, such as switch stack or Cisco Stackwise Virtual Pair, SVP, or the less preferred single highly redundant physical switch. One advantage of this design is that spanning tree dependence is minimized and all uplinks from the access layer to the distribution are active and passing traffic. Even in the distributed VLAN design, you eliminate spanning tree blocked links because of looped topologies. You reduce dependence on spanning tree by using Ether channel to the access layer with dual homed uplinks. This is a key characteristic of this design, and you can load balance up to 8 links if needed for additional bandwidth. At the same time, multiple links in an Ether channel have better performance characteristics versus single independent links. So here we have a simplified distribution design with a VLAN per access switch. So each access switch has its own VLAN. The access switch here gets VLAN 30, here gets VLAN 40. So you can do that, or assuming I have my place, I do. You can have a simplified distribution design with VLANs spanning access switches. So here you'd have like a layer 3 boundary, but here it's just a layer 2 like that. Ether channel is a logical interface that can use a control plane protocol to manage the physical members of the bundle. It is better to run a dynamic channel protocol instead of using forced on mode, because a dynamic channel protocol performs consistency checks for interfaces programmed to be in the channel and provides protection to the system from inconsistent configurations. Cisco Catalyst switches provide both port aggregation protocol, BAGP, which is a widely deployed Cisco designed protocol, and link aggregation protocol, LACP, which is based on IEEE 802.3AD open standards. There are several other advantages to the simplified distribution layer design. You no longer need IP gateway redundancy protocols such as HSRP, VRRP, and GLBP, because the default gateway is now on a single logical interface, and resiliency is provided by the distribution layer switch or switches. Also, the network will converge faster now that it is not depending on spanning tree to unblock links when a failure occurs, because Ether channel provides fast sub-second failover between links in an uplink bundle. The topology of the network from the distribution layer to the access layer is logically a hub and spoke topology, which reduces complexity of design and troubleshooting. The hub and spoke topology design provides a more efficient operation for IP multicast in the distribution layer, because there is now a single logical designated router to forward IP multicast packets to a given VLAN in the access layer. Finally, by using a single logical distribution layer design, there are fewer boxes to manage, which reduces the amount of time spent on ongoing provisioning and maintenance. Using the Cisco Catalyst 9000 series switches for physical or logical stacking is also the basis for enabling resiliency features such as stateful switchover, SSO, nonstop forwarding, NSF, and in-service software upgrades, ISSU. Okay, so another way you can configure your network is, instead of a design like this, you have a design that looks like this. And that's not to say that you get that design by deleting one of these devices. Instead, you stack them together. You use something called stacking to make these two devices logically behave as if they were just one device. And then you set up port channels between these devices, and you set them up, so you hook them into each device, and then you set up a multi-chassis port channel to a single port channel here. So you end up with what looks like that. And this we can see, very simple, very easy to understand, much easier than that. Just requires stacking though. So I'm gonna spend a little bit of time seeing if I can do this quick. If I can do it quick, that's good. I have a feeling it might be a little bit more time consuming than I'm giving it credit for. We're already at the 2-hour mark almost, so we'll just give it a shot, see what kind of commands there are. We'll try create stacking. So I don't see any create stacking. Let's do configure stacking. Okay, we got it. Perfect. So Initially configure all nodes in a new stack. So easy setup. Method is not implemented on this platform. Configure stacking. Slot 1. Well, slot 3 actually. Right? Method is not implemented on this platform. See, I don't think I can stack using these extremes. I don't know why I thought the extremes would be good for the. Oh, you know what? It's because the line rates. So if I do configure port, and then I do all, and then I do or show. Yeah, we can see all these speeds we're capable of. So let's set it to 50 gig. Duplex full, of course. Oh, you know what? We don't. That's just what the OS says. So I bet you we don't have any of these higher than 1 gig speeds. Oh, it's not supported on. Yeah, oh yeah, it looks like we're not even capable of a gig. So that's pretty lame. Yeah, that's super lame. Okay. Yeah, so these extremes belong at the edge, and then these Arubas belong at the distribution. The Arubas are capable of 1 gig. It looks like the extremes are only capable of 100 meg, so definitely not an appropriate choice for the distribution. I picked them for the distribution because I thought they could support any of these speeds, but clearly they cannot. Well, let's verify that the line rates on these can go to 1 gig. Not supported. Oh. The heck is half? Why is it not supported? What about like on port 4? Not supported. Okay, well that's weird. None of them are supported, so yeah, I guess I'm not sure. Let's do a show hand. Oh, okay, yeah. So we do have 111 up with a link speed of 1 gig. Although I thought there was a link speed of 1 gig on these as well. No, it's 100. Yeah, so we're going to need to swap these up and use our extremes down at the edge, which will be better anyways, just the way that you can't configure ports with IP addresses on the extremes, but you can with the Arubas. The Arubas will be better off in the distribution layer just because of that. But in addition, it looks like we can do 1 gig ports on Arubas, but we can only do 100 meg ports on the extreme. So definitely that means that that we would want the Aruba in the access layer. But we should have, there should be some ports capable of 1 gig. Okay, it's not supported on 9. What about 10, 11? Yeah, I don't have a port 20. Yeah, okay, so do I have a port 16? No, because I think it'll be supported on the last port, the highest number port that it has. Oh, nope, not supported on port 12. We already tried that. What about the lowest port? Not supported there either. Not supported. Not supported. Okay, speed 100 is supported though. Yeah, so it looks like we don't have any 1 gig ports available on this extreme. That's kind of a shame. I wish we had, it'd be nicer if we had a gig port so we could use that for our uplinks to the distribution layer and we'd have better oversubscription ratios. But it's not the biggest deal in the world, and it's definitely not a reason to have it up in the access layer. I think it's even more reason to have it in the distribution layer. I think it's even more good reason to kick it down from the distribution layer to the access layer because it only supports 100 meg speeds. So what we can do is we have our port channels, but we can like add links to those port channels. I mean, our port channel is going to be 200, so we'll have a ratio of 200 to 200, so 1-to-1. Because right now we've only got 2 devices, 2 uplinks, so we have a 1-to-1 ratio, which is 20-to-1. Actually 4-to-1 here would be the oh no, here's where you can have it 20-to-1. You'd only want it 4-to-1 from your access to your core. Oops. Yeah. Okay, so I think that's going to be it for this video. Next video, I will be going back and doing some hands-on to set up stacking. I think we're gonna demote the extremes down to the access layer because they're only capable of fast Ethernet 100 ports, and we're going to promote the Arubas up to the distribution layer because they have gig ports available, and then we'll work on stacking the Arubas together instead of the extremes. I think I'm probably going to have some more luck with that. Alright, so thanks for watching this video, and I'll see you in the next one.